In a typical sedan, they sit low and the trunks are deep, which is not conducive for people with back problems. It makes it difficult to get things in and out. With our cargo lift, it moves the trunk up into a more ergonomic position, making it easier for people with back problems to get stuff in and out of their trunk. When designing our mounting system, we wanted to take advantage of the existing spare tire mount to eliminate any need for modification or drilling into the vehicle itself. We utilized all-thread and some all-thread couplings. This makes it very simple to remove. For our design, we chose to use a lead screw setup, which allows us to convert the torque from an electric motor into linear motion to actuate our cargo lift.
For prototype purposes, we chose boxed aluminum for the ease of machining, while still being rigid enough in its boxed form. For the sliders, we used pre-drilled angle iron because the pre-drilled holes made it easy to create a slot. We chose steel to retain its rigidity when the slots are made.
Additionally, the input link shares a common pin with the slotted pin to allow the input link to stay on the same plane as the motor raises the trunk. When designing our mechanisms for its desired functions, there were a few iterations to our model. Our first model looked something like this. We thought this was good, but upon further examination, we realized that both the functions of retracting and coming out would be difficult for the motor as it crosses this 90-degree angle. Our second iteration of the mechanism looks something like this. It's very similar to the first design, but the input link is found on the trailing arm instead of the leading arm. While this is more compact and about as strong as our last model, we realized that the throw of the input link was far too much for our motor to handle, so we opted to redesign for a third iteration. Our third and final iteration of our project had its links oriented like this. This proved to be the optimal design for our objective because it would be considerably easier for the mechanism to retract than it would be for it to come out, which is beneficial because in our application, the cargo would only be placed on the trunk deck when it's in its extended position. This design is also fairly compact, and it only struggles in one direction, where some of our previous designs struggled in both directions. When designing our mechanism digitally, we knew that space was going to be a big constraint because we wanted to fit the whole assembly in the spare tire compartment, so the liftable trunk would naturally rest in its original position. Because of this, we first modeled the trunk to its appropriate dimensions. When designing the mechanism, we realized that there was an inverse relationship between the mechanical advantage and the translation of the mechanism. In other words, the easier it is for the motor to move the mechanism, the less it's going to come up and out of the vehicle. Because of this, we tried to keep the mechanical advantage as close to 1 as possible so that the required range of motion was met. The overall length of the mechanism was chosen because there's another inverse relationship between the length of the mechanism and how wide the legs could be mounted apart. As demonstrated here, since it's radius on this end, the longer that we make these links, the more inward they're going to have to be, which means that the mechanism could easily topple over if weight is put on the edges. Additionally, when digitally designing our mechanism, we also took into account the thickness of the frame that the mechanism would be mounted to, and the back spacing that the mechanism would need for the motor to have its full range of motion.